Good morning. I am Hyun Kim, and I am master candidate from the Department of Biomedical Systems Informatics at Yonsei University. Today, I'm going to talk about my research, personalized progress federated learning with leveraging client-specific vertical features. So here are the contents of this presentation and abstracts. The personalized federated learning for consistent training, personalized models to adapt to diverse data distributions in federated learning manner. On the other hand, conventional horizontal federated learning cannot leveraging vertically partitioned features to increase model complexity, and vertical federated learning requires all clients to share a large number of overlapping sample IDs. In this paper, we propose the personalized progress federated learning, a multimodal personalized approach that allows the leveraging of client-specific vertically partitioned features. We empirically tested PPFL on a real-world public electronic health record dataset. The experimental results demonstrated that PPFL and its variants outperformed compared to the other based models by not only leveraging the common feature space, but also training individual clients and their specific feature space. Another important result is that the proposed model improved the robustness of the unseen data distribution. So this is introduction. And federated learning is a machine learning setting where multiple clients collaborate in solving a machine learning problem under the coordination of central server or service provider. So each client's raw data is stored locally and not exchanged or transferred. Instead, we focus the updates intended for immediate aggregation are used to achieve the learning objective. So it aims to solving the problem of data leakage while preserving privacy in distributed environments with communication efficient manner. The design of federated learning can be categorized based on how data is distributed among various parties in the feature or sample IDs. So horizontal means that the data are divided according to the sample space with the same feature space. And vertical means that when the sample ID of data is the same, the feature space is stored differently. So horizontal federated learning aims to build generalized model using a large number of samples collected from multiple clients. And vertical federated learning, on the other hand, is aimed at improving the model complexity by exploiting more feature information stored in multiple clients. And in this slide, I will introduce the data heterogeneity and non-IID setting on federated learning. So machine learning techniques basically have an IID assumption. Then each data is an independent and equally distributed random variables. The IID assumption in the federated learning assumes that the distribution of data held by each client is independent and identical. However, in real-world data can have different input and label distributions of data. So here is the list of non-identical client distributions, such as feature distribution skew, label distribution skew, same label and different features, same features and different label. Real-world federated learning datasets likely contain a mixture of this effect. There are several prior studies that have studied the problem of FL model in this non-IID setting. Traditional federated learning model have lower performance in non-IID environments. When the data is heterogeneous, the weight of the global model doesn't converge properly. This means that the combined global model is very different compared to the results of individual client K. Also, in other previous studies, heterogeneity makes convergence itself difficult in the FL model learning processes. Therefore, it is essential to adjust the learning rate decay. So, there are two purposes of this study. First, overcoming the limitations of design based on horizontally and vertically partitioned data. Horizontal federal learning cannot be exploited even if there are important features that are not shared for a specific client. And vertical federal learning must have sufficient overlapping sample IDs on multiple clients. The second is overcoming the performance degradation of federal learning on non-IID setting. So the proposed model is focused on building personalized model that balances between generalization capabilities with common features and client task specific knowledge with client specific vertical features. Here is the problem setting. Suppose that an individual client K has dataset D and is consisting of M samples. For different distributed clients, there are common feature vector X with feature space P and vertical feature vectors with Q dimension, and this notation is S. P is identical for client K because there is the common feature for horizontal federal learning, and Q might not be identical across all clients. The goal of PPFL applied in federal learning is to personalize the prediction of the target vector Y for specific client K and enhance the prediction performance, allowing individual clients to expand the model with their specific vertical feature information S. The proposed model consists of two main steps. The first step is to learn the horizontal federal learning model using only the common feature data with distributed clients. And second step is for personalization. The global model learned from the server is deployed to each client. An additional subnetwork columns are created inside the client to receive client. Vertical net is created to receive client-specific vertical information, and the personalized net is created to receive and aggregate existing global models and client-specific vertical networks. So I will explain the first step. The first step is to learn the horizontal federal learning model. In this step, model learns the global information for multiple distributed clients for the common feature space. In this study, we use the FedAvg algorithm. However, the aggregation schemes can be replaced by any other aggregation algorithm for the federal learning. The second step is to proceed when the horizontal federal learning model on the previous slide is deployed on a specific client. It is composed of three network columns: horizontal net, vertical net, and personalized net. Each layer of horizontal net and vertical net is connected to personalize the net through lateral connections. In horizontal net, the internal weights C prime were initialized from horizontal Federated model in previous slides. These parameters freeze to prevent training during personalization. This is to prevent forgetting the global knowledge of FL models learned for existing common features. And vertical net is a network column to allow learning the client-specific vertical features that is created to expand the model's feature space. Each parameter of personalized net calculates the output values of each layer from the two network columns and its previous layer through the lateral connection. Lateral connection is a method to receive the intermediate results from different network columns as input for a specific network layer. So in the conventional neural network model, if the connectivity between layers occurred in just feed-forward method only within the column of network. The final output is calculated at the last layer of personalized net, where softmax, rel, and linear functions can be used depending on the task. The objective function is as follows, and you can see the parameters for optimization. Parameters are learned except for internal weight of horizontal net C prime, as I mentioned before. In summary, the lateral connections C and V learn how much of the existing globally learned knowledge to fit the task of a specific client and how much of information in client-specific vertical features. Personalized net combines this information to conduct the inference. The entire PPFL learning processes can be represented as a two-step algorithm. So algorithm 1, to learn the horizontal federated learning model, local models are created using common feature vectors from each client. Horizontal networks are learned by aggregating weights of federated learning models globally and repeating them as T communication rounds. And second, to learn the PPFL model, algorithm 2 learn inside a specific client when horizontal federated model deployed to client. Algorithm 2 is started by initializing and freezing the parameter C prime of horizontal network in algorithm 1. And in this process, vertical net for levelizing the client-specific vertical features and personalized net for the final inference are created and trained. If a specific client does not have a vertical feature vector, then it is trained by forming a PPFL model, excluding the weights in the vertical column, like V and V prime. For the experiments, a data set of public HR data Physionet Challenge 2012 was used. This data set is consisting of 8,000 ICU records and 4 ICU types. Demographics and procedure were used as a common feature, and lab tests and vital signs were used as the client-specific vertical features. In real-world setting, the client-specific feature may be different for all clients. However, in this study, the identical client-specific feature was used for comparison in this experiment. We predicted in-hospital mortality and length of stay as target results. Each ICU is assumed to be a client in a distributed environment. Train, valid, and test set were configured at a ratio of 6 to 2 per client in a total sample of 6,000 records. In addition, an external ICU was configured with a sample of the remaining 2,000 records. The training set was used to run the model, and validator set is used for hyperparameter tuning. When analyzing the statistical description of demographic features by ICU, we found that the difference of distribution by client is statistically significant for both demographic variable and outcome variable. This slide shows the comparison model to evaluate the proposed model. First, X means learning only the common features, and X, S. The common features and client-specific particular features are used for training. The FedAvg and FedProx model is a federal learning model across all clients. PPFL learns on individual clients by leveraging only common features. PPFL S learns on individual clients by leveraging both common features and client-specific particular features. The local models are multi-layer perceptron model, learned only a specific client. So the local model was learned within each ICU. The federated model was learned from the all clients. And PPFL model was personalized to specific clients after federal learning. And these results are evaluated on external data set. The PPFL models outperformed the internal X, FedAvg X, and FedProx X in average of AUROC score. PPFL S showed the highest performance for every ICU clients on external validation. The results for PPFL S show that the overall performance of PPFL S outperforms both internal validation and external validation. So our proposed model without client-specific particular features could be personalized for individual client, and our method successfully allowed the expansion of feature space of the model learned globally in a federal learning manner. And our model is robust to distribution of unseen data, which is not federally learned, and even after personalization. Our underlying assumption was that when personalizing a learned federal learning model, the proposed model would prevent the knowledge forgetting through multiple clients from the and compared to transfer learning. In the first figure, an experiment was conducted using only the common feature with the PPFL model, the PPFL model without freeze, and transfer learning model. It was personalized with trained data of each client and evaluated as an external client. Both without freeze PPFL model on green line and transfer model blue line includes in loss with epochs, but in the case of PPFL the yellow line, stability can be observed in the learning process. The next figure is an experiment when vertical feature is included. Experiment with only two models because traditional transfer learning cannot expand new feature space. The performance of without freeze model in yellow line is slightly inferior in client 3 and 4. And the performance are similar for client 1 and client 2. The convergence of without freeze model is greatly divergent. Note that client 2 has the most different input distribution and lab distribution with the external client, and also has the largest class imbalance. There is the effectiveness of this model shows good results in clients that differ significantly from the overall data distribution. Although the vertical features has more information than the common feature, the effectiveness of the proposed model is observed. And we investigate the concept shift of our model after applying PPFL. We computed feature importance through the sharp value. Within common features, age and mechanical ventilation features had highest sharply value in all clients. And in the PPFL model, after expanding the feature space, the GCS score had the highest mean absolute sharply value for all clients. The previous experiment was conducted by setting with identical client-specific features for comparison. However, in this slide, in this experiment, we evaluated on different client-specific vertical features across the clients. Even in different client-specific vertical feature setting, our model showed high performance in both internal and external evaluations in average of AUROC score. So in conclusion, we have proposed a personalized progressive federated learning algorithm, which allows federated algorithm to become personalized for heterogeneously distributed clients and expand the feature space for client-specific vertical features information. In PPFL, we use the federated model to train globally learned knowledge from common feature information and create vertical network to learn the client-specific vertical features. We then use the lateral connection to create personalized network, which allows the integration of globally learned information and client-specific vertical feature information. So we investigated the performance improvement and robustness of public real-world EHR data and validated the usefulness of our proposed model. So that's all I have prepared for you today, and thank you for your time.